Hello everyone, welcome to this week's Data Structures Lab on trees. I am Madhumanti Das, and in this lab we will specifically learn about binary trees and binary search trees. As we know, a tree is a structure made up of nodes connected by edges. So what are binary trees? A binary tree is a tree which can have at most two children or subtrees, which means each node in a binary tree can have 0, 1, or 2 children, but not more than 2. Here is an example of a binary tree where A is called the root node. B and C are typically named respectively the left and right child of A, and A is called the parent node of B and C. Same goes for the nodes D and E. They are the left and right child of B, and B is the parent of D and E. G is the right child of C, and C is the parent node of G. Now in this lab, to work with binary trees, we first have to construct a binary tree, and then we will use the tree to complete the lab task. How do we represent a binary tree? We can create the nodes of a binary tree where we take the elements manually or through user input and link them, or we can also take the elements of the binary tree from an array and then construct the tree. I'll show you both. Here I have taken a sample binary tree and we will try to construct it as it is. So first we have to create a node class where we will take the following attributes. We'll take an element. We'll take the left and right node, and we'll also take the parent node. We will then create the constructor. And we will set the values. Then we have to create the main class. In the main class, we will create nodes and take the elements manually or from the user. As there are 6 nodes in the sample tree, we will create 6 nodes in the main class. We'll take the first node as root, and we will write the first element. And we'll keep the rest, the left, the right child, and the parent null for now. Then we go on creating the other 5 nodes the same way. After creating the 6 nodes, now we have to link them. How do we do that? First, we link the root node to its left child. So root.left is equal to n2 and n2.parent is equal to root. We do the same for its right child. So we write root.right is equal to n3 and n3.parent is equal to root. Now to create the child of n2, we write n2 dot left is equal to n4 and n4 dot parent is equal to n2. We create the right child of n2, hence we go on writing n2 dot right is equal to n5 and n5 dot parent is equal to n2. We do the same for linking the right child of n3. So we write n3 dot right is equal to n6 and n6 dot parent is equal to n3. As there is no left child of n3, we do not have to create it. Now I will show you how you can construct the tree if the elements are given in an array. In the array representation of trees, Each node is represented by a specific index of an array. So the root node is kept at index 1 and its left and right child in indices 2 and 3. Hence, we can derive a relation from this that any node at index I will have the left child in index 2i and its right child in index 2i plus 1. So when we keep the root node at index 1, its left child is in index 2 and the right child is in index 3. Similarly, the node at index 2 will have its left child in index 4 and the right child in index 5. As the node at index 3 does not have a left child, so index 6 will be kept null and the right child will be in index 7. Now, if we fill up this array, it looks like this. So in the array representation of binary trees, there is a lot of space wasted unless the tree is complete, which means that all the levels of the binary tree are filled. So let us try to construct the tree from an array in code. Again, we have to construct the tree in a main method. I have taken the array like I have already shown you, and we create a recursive method to construct the tree. So I write a static method which will return the root node. I pass the array as the parameter and also the first index. Then we start creating the nodes. So then we start creating the nodes. So I write node root is equal to new node. And we take the element of the array as the element of the node and the rest are kept null. To create the left and the right child of the parent node, we'll recursively call the method again. We'll pass the array as a parameter and also the index will be 2i as I have explained before. We'll do the same for the right child. And for the right child, the index will be 2i plus 1. After we are done specifying the left and right child of a node, we also have to link them to their parent. So we write when the left child is not null, its parent will be, so root.left.parent is equal to root. Similarly, when the right child is not null, root.right.parent will be equal to root. And we have to then return the root. As this is a recursive method, we have to have a base case. So we write a if function whenever I is less than 0 or I becomes greater than or equal to the length of the array, or whenever the element of an array is equal to null, we will return null. And else we will do this. Now, as we are done creating the recursive method of creating the array, we have to call it from the main method. So we write node root, we call the method, pass the array, and also the first index. Now, as we are done with constructing the binary tree, we can now move on to our lab tasks. For the first task, we have to calculate the height of a binary tree. The height of a tree is the maximum height of the root subtrees plus 1. We add the 1 to consider the root node or the current node. So if a tree has one node only, the height will be 1, and if it is an empty tree, the height will be 0. In this case, the height of this tree is 3, as the maximum depth or height in the left or right subtrees is 3. If the tree looks like this, we can see that the maximum height is up to this node in the right subtree. So the height of this tree will be 4. We can create a method to calculate the height of a tree in the same class, or if you want, you can create a separate Java file as well. I'll create a method in this class. So the return type will be an integer, and I'll pass the root node as the parameter. And the base case will be, as I have mentioned, if the root node is null, which means that if it is an empty tree, we will return 0. Else we'll return 1 plus, we'll calculate the maximum height of the left node and then the right node. So to find out the maximum, we have to create a separate method which will give us the maximum depth from the left subtrees and the right subtrees. So if the depth in the left subtrees is greater than the right side, we'll return L, else we'll return R. Now in the main method, we'll print the height of the tree that we have created. We want to print height of the tree, and we'll call the height method, and we'll pass the root node as a parameter. And when we execute this code, so we can see, as I have said, the height of the sample tree was 3, so it gives us the desired output. For the second task, we have to calculate the level of a given node of a binary tree. So the level of a node in a binary tree is 1 higher than the level of its parent. So the level of the root node will be 0, and it will be 1 and 2 respectively for any of these nodes. To code it, we'll take a method named level, and we'll pass a node to calculate its level. And if it's a root node, that means if its parent is null, we'll return 0. and we will return 1 plus level of its parent. We'll call the method again recursively. Now to print the level of any given node, we'll call the method from the main class. We'll call the method and pass any node as a parameter. So the level of this node should be 2, and as we execute it, we get the desired output. Now let's move on to binary tree traversal. We can traverse a binary tree in 3 ways: pre-order traversal, in-order traversal, and post-order traversal. So in pre-order, it first visits the self node, then the left node, and then its right node. In order, it first visits the left node, then the self node, and then the right node. In post order traversal, it first visits the left node, then the right node, and then it visits the self node. To simulate pre order traversal, we'll write SLR over each node of a binary tree, where S stands for self and L and R stands for left and right, respectively. We'll do this for each node, and then we will start traversing it. Starting with the root node, we first visit self in pre-order. So we will print 10 first. We move on to its left side. We visit self again. We print 5. We move on to its left side and we again visit self. So we print 17. And as the node 70 does not have a left and right child, we can cut these. As we go back to node 5, we can say that the left side is done visiting and we can move on to the right side. Coming to the right side, it first visits self, so we print 9. We can cut L and R as there is no left and right child. And we go back to 5 and we can say that the right side is done visiting. We go back to the root node 10 and cut L. We move to the right side. The node 7 will first visit itself, so we print 7. As there is no left child, we cut this and we move on to the right side. It will first then visit itself, so we'll print 28 and we can cut L and R as there is no left and right child. We can also cut this as we are done visiting the right side. And when we go back to the root node, we can cut the R as well. Now this will be the output of pre-ordered traversal. To code this, we will take a static method and we'll keep it void. And we'll first pass the root node as the parameter. So we will not traverse a node if the value of the node is null. Hence we keep a condition that if R is not equal to null, only then we will traverse it. We will first print the element, which means that we are visiting self. So R dot element, it means we are visiting self. Then to visit the left subtrees, we will call this method recursively and it will visit the left subtrees. And to visit the right subtrees, we'll again do the same thing and pass the right child or right subtree as the parameter. So how does this work? It first checks if a node is null or not. If it is not, to visit self, it prints the element, then it visits left, and then it visits its right subtrees. So to call this from the main method, we write pre-order traversal and we pass the root node as a parameter. As we execute this, it prints all the elements of the binary tree through pre-order traversal. We can see that the result is the same as we found in the simulation. Moving on, we will also learn about binary search trees in this lab. A binary search tree is basically a binary tree with some additional properties, which are: if I consider the root node, all elements in its left subtree must be less than the element of the root node, and all elements in its right subtree must be greater than the root node's element. We also have to be careful about each left and right subtree must also behave like a binary search tree, which means if I consider this node, all elements in its left subtree must be less than this element, and all elements in its right subtree must be greater than this element. It goes the same for this node. We can see that the right subtree of this element is greater than this node's element. To construct a binary search tree from an array, we will first take the first element of the array as the root node. As we move on to the second index, which is 5, we will check with the root node, and if it's less or greater than 10. As 5 is less than 10, we will place it on the left side of 10 as its left child. When we find 7, we will again start checking from the root node. So 7 is less than 10. We come to the left side, which is 5. So 7 is greater than 5. Hence, we place it on the right subtree of 5. When we find 15, 15 is greater than 10. So we place it on the right side. When we find 3, 3 is less than 10. 3 is also less than 5. So we place it here. When we find 12, 12 is greater than 10 but less than 15. So we will place it on the left side of 15. And when we find 25, 25 is greater than 10 and also greater than 15. So we place it here. And that is how we construct the binary search tree from an array. For the lab tasks with the binary search tree, we have to search for an element in the tree, and we also have to print the elements of the binary search tree in a sorted order. So search operation in binary search tree will work something like this. Let's say we want to search for a number 3. What we have to do is we'll start comparing from the root node, and then we will compare the value of the root node with the value that we want to search. So if they are equal, we are done with the search, but if it is lesser, then we need to go towards the left subtree, and if it's greater, we have to move towards its right subtree. Because in a binary search tree, all the elements in the left subtree are lesser and all the elements in the right subtree are greater. So now as we want to compare the number 3, we see that 3 is less than 10, so we move on to its left subtree. We also see that 3 is less than 5, so we move again to its left subtree. And then we see that 3 is equal to the left subtree of 5, and then we can be done with the search. To print the elements of a binary search tree in a sorted order, what we have to do is we will traverse the binary search tree with in-order traversal. To simulate this, we will write LSR over each node. As in order traversal, we first visit the left node, then the self node, and then visit the right node. So to start traversing from the root node, we first visit the left node of the root node, which is 10, and then we move on to 5. And as 5 also has a left child, which is 3, so we will now check if 3 has a left child. As 3 does not have a left child, we can cut this and then we will visit self, which means we will print 3, and we can also cut R as 3 does not have a right child. When we go back to the node containing 5, we can cut L as we are done visiting its left subtree. We will then visit self, which means we will print 5, and then we will move on to its right subtree. The right subtree, which means the node containing 7, does not have a left child, so we will cut L. We will visit self, which means we will print 7, and then we will also cut R as it does not have a right child. We go back to the node containing 5, we cut the R as we are done visiting the right child. We go back to the root node and we can cut L as we are done visiting its left subtree, and then we visit self, which means we print 10, and then we move on to its right subtree. Coming to the node containing 15, we first visit its left subtree, which is the node containing 12. We cut L as it has no left subtree. We visit self, which means we print 12, and we can also cut R as it does not have a right child. We go back to the node containing 15, we cut L, we visit self, we print 15. We go to its right subtree, which is the node containing 20. We cut L as it has no left subtree. We cut S and print 20, and then we can cut R as it has no right subtree. We go back to 15 and we can also cut R. We go back to the root node and we can also cut the R. And we can see that the output is in a sorted order. So to summarize, this is your lab outline for this week. I have already discussed how you can calculate the height of a tree and calculate the level of a node in a tree. I've already discussed about how you can print elements of all nodes of a tree using pre-order traversal. I hope you'll be able to do in-order and post-order traversal on your own. For task 6, you have to evaluate whether two trees are exactly same or not. For that, you have to create two binary trees and compare between them. In task 7, you have to make a new tree, which will be a copy of a given tree. I have also discussed and simulated task 8 and task 9 for you, where you have to search for an element from a given binary search tree, and you have to print all the elements of a binary search tree in a sorted order. So that is all for this tutorial. Thank you and good luck.